Let's start. Now, armed with those two formulas, let's see if we can get some problems correct. So you have this one in front of you. The copper pipe has an outer diameter of 40 millimeters. Notice it's like a pipe screwed into the wall. And an inner diameter of 37 millimeters. And it's tightly screwed to the wall. And 3 torques are applied to it. 3 different torques are applied to it. Determine the absolute maximum shear stress developed in the pipe. Now, again, at a glance, doesn't that look weird? Like, how would there be 3 different torques? I can imagine somebody putting a pipe wrench on it somewhere and going and like torquing it down, but it's like, how would you have 3? It's like, are there 3 people competing with each other? Well, we can argue about that, but whatever. Let's stare at the kind of the sections of this though. Would you agree that everything in here is 80 from the previous section? If I section just that part, all of the metal that's in there thinks it has 80 on it. Do you agree with that? But what does this stuff think? What is that? What do those people think? Like,
80 minus 20, yes.
Yeah, notice they're going opposite directions. If they're going the same direction, it'd be 100. If they're going different directions, it's 60. So actually, that part of the pipe isn't wanting to twist near as bad, right? And then what about the one at the end? What about this last section over here? What's it think?
90.
80 minus 20 is 60, plus 30 is 90. So notice that section actually is the one that's going to break. Does that make sense? If you twisted it hard enough that the metal just went and folded, that's where it's going to break. Do you agree with that?
So I kind of, when I was looking at this, I just kind of assumed this pipe was going to have different, like in between the 80 and the 20, that pipe, the inners were going to have like 60. And then in the 20 and the 30, it would have like 10. Like I thought the pipe was going to act differently.
Yeah, I get it. In other words, the 30-20 area doesn't know 80 exists. Yeah. And that's not obvious at all. I could totally see that being the case.
So the pipe kind of acts as one.
Yeah, but because it's connected, it is working its way through over there. So yeah, that's not obvious at all. So notice what it asked. Yeah, that's exactly right. Because of that, it's going to break somewhere in here. Now, assuming the threads made it skinnier through there, you'd think it would break where the threads are. Does that make sense? Because the radius of the pipe actually is kind of screwed up in that section. They're asking us to ignore that. But if it's going to break, it's actually going to break somewhere in here. Because it's the same pipe all the way through, and that's the place that has the most torque on it. So
kind of like a gruesome thought, but I was just thinking if you like held your arm out and someone twisted it this way, that way,
exactly,
this way, it's going to break at your shoulder. That's a weird. I just wouldn't think that.
I don't want to think about it.
Well,
think about it.
No, that's good because basically you're out here doing 80, right? And your shoulder is wanting to break because it is fixed there, right? Now, is it going to break? Do you see how my arm is able to rotate without my shoulder changing? That's exactly what material can do. Good. It didn't break over here. It's good this wasn't super rigid, right? Don't I want this to be nice and rubbery if I want to bend this? And so notice it's having to twist to do that. But if I keep going, at some point it is going to break, right? Where is it going to break? Where it's attached.
Okay, that makes sense. So it doesn't matter how many like extra forces, the overall force happens at the attachment point.
Yeah. Now, so if I'm over here and I'm like I'm about ready to like break your arm or whatever, then somebody else comes in and they say, oh, isn't that helping? I'm trying to, your arm's about ready to break off, and somebody comes and says, now this isn't going to break.
Yeah.
Because I'm pulling back, right? So now it's only 60. It was 80 and 20 got released. Now it's only 60. Ooh, it feels like relief. Now, could it break in there? Sure.
Yeah, that's what I was thinking. I thought it would break right here. I thought it would break in between the 80 and 20.
Yeah, and there's a part of me that looks at that and says, isn't that 100 then? You know what I mean? Because it's like, if it's 20 going one way and 80 going the opposite.
It felt like 100 on my arm.
Yeah.
It felt like it was more.
Yeah.
Like that doesn't feel good, huh?
Yeah.
But then if you just like. Yeah, well, I know, but it's less. Okay, I'm sorry. all.
That makes sense.
No, this is good. This is exactly what we want to do. We want to reason about this. Now, because this said here, this key word is maximum shear stress, then we have to look at this pipe and say, well, where's the biggest torque possible? Remember, our formula is just that the shear stress is equal to torque times C divided by J. And they only wanted the maximum. They didn't say, I want all of them. They just said, give me the maximum, which makes sense because the maximum is what's going to cause this to break, right? So because of that, I only have to do the 90 because it's the biggest one there. So I'm making a note to myself. This is the T max based on the sectioning concept. And I am interested that you see this as the same thing we did before. Before we were sectioning up our pipes, but it was always axial forces that were pushing and pulling on it. Well, it's the same thing here. It's just now they're twisting forces that are pushing and pulling it, but we're still having to section it to see what's happening to each chunk.
Is that PSI? No.
I'm sorry, what?
What's the units of that?
Love it. Wonderful question. So because it's torque, what do the units have to be? Torque is a force times the distance. So it's either newtons, meters, or it's foot-pounds. In this case, I see metric, and it's like, oh yeah, Newton meters. That makes sense because it's a force times the distance. So I don't know what the force and the distance are because they just already multiplied it out for me, I guess. They just told me it's 30 or 90 or 60 or whatever. Okay, so, because I'm after max, then cool. And notice the formula says tau max is what this formula is designed to do. So I have 90, and of course, because this is early, I feel like I better leave Newton meters in it to kind of see what my units will be in the end. So I have 90 Newton meters. C was, again, the maximum radius, right? It wasn't just any old radius. It was the maximum radius. Now, that maximum radius, we were told, even though this is hollow, this is, well, it's not C because that was a diameter, but because the diameter is 40, then the radius is 20, right? And so even though this is hollow, that C is still a C. It's still maximum. It's the outer edge because that's where the most torque is going to be, whether there's a hole in the solid pipe or not. So that's 20 millimeters. Now, again, should I leave it 20 millimeters or because the other one's in meters, should I turn this into meters? I'm not really sure. I think I'll just call it meters for now. We'll see if that was a good idea later on. So I changed 20 millimeters to 0.02 meters. And then I'm dividing by J, right? But what is J? Well, in this case, because it's hollow, does it make sense we need that second formula? J, what is J? What is the second moment of inertia? What is this shape? What is this shape's desire to not rotate, if you will? It's pi over 2 times the outer radius, which was 0.02 meters raised to the 4th power, minus the inner radius. Oh, that's terrible. What's half of 37? I guess that's 18.5. And then if I move the decimal point 2 places to the left, I guess it's 0.0185. Are you cool with that formula? I mean, you're looking at your note sheet going, yeah, that's what that sheet says, outer minus inner. So this was hollow. And so I like this equation because everything on the right side is numbers. Now, before we do this, though, stare at the units of this. Can you tell what the units are going to be? The bottom is meters to the 4th. The top is Newton meter meters. So what's the unit of the answer to this going to be?
Meters squared.
Newtons over meters squared. You agree with that? Because there's 4 meters on the bottom and 2 on the top. Do we have a name for that? Have we seen that before?
Is it Pascal?
No. Yeah, Pascal.
I think this is clear back on your first notes, actually. Yeah, PSI is pounds per square inch. So force on the top, inches squared on the bottom, length squared on the bottom. This is the same thing. Force in metric is newtons. This is a Pascal. Yeah. So because that's a crazy unit, somebody said, let's rename it, but the units are newtons per square meter, which is just pascals. So this is a unit we saw before, but actually this was listed actually on your first note sheet back when we learned about shear stress in the first place. So that actually makes sense that that'd be the case. Now all I gotta do is just punch those numbers in. 90 times 0.02. Again, be careful dividing by pi over 2 because that's really actually dividing by a fraction. So you're really multiplying by 2 over pi. Be easy to type this in wrong and screw it all up. If you don't get this wrong, you actually get I guess I'm going to have to type it in because I wrote Newton meters squared. So I'll just give you a second to think about it. 90 times 0.02 times 2 divided by pi divided by parenthesis 0.02 raised to the fourth minus 0.0185 raised to the fourth. Close the parenthesis. I got 267.33168. What's the back of the book going to say for this?
26.7. Oh, it'd be 2.67 megapascals. Is that it?
Yeah, is that right?
We're missing an 8, 3.
I'm missing an 8. There was an 8 there.
Yeah, so 26.7 megapascals.
Yep. So we moved it 6 places, which was mega. So like that's what you'd see in the back of the book, but these are both correct, right? Now, can you appreciate material? Like because we converted this not to newtons, not to a force, but to newtons per square meter, does it make sense if this is something you could look up? Like how much, if you twist on something, how much can A36 steel, how much torsion can it handle? And keep in mind, it doesn't even have to be torsion. It's just how much desire to slip one piece to slip past another piece. How much desire can A36 steel handle, you know, there? Is that something we could look up? Now, interestingly, I think if you look in the table, it's not one of the options.
Well,
or it's an option, but it was like nothing there.
It would be shear, right?
Yeah, it's like there's a spot for it, but they didn't put anything there, which actually I don't know why. I just discovered that today. I was like, what?
Is that because it depends on like the thickness, maybe?
I don't know.
Oh.
Because there's one problem we're going to do in a few minutes where they told us the value of that. And then I thought, well, why didn't we just look that up? Because it said it was, I looked in the back and it like wasn't one of the options. So
there was one homework problem that gave us an value for aluminum, but I was looking at it at the back of the book and it was a different value. And I got furious because I was like working on it for like an hour and I was like, why can't I get this right?
Yeah.
Because I used the one in the back of the book proposal.
Oh, geez. Yeah, that's super frustrating. But the cool part of this is somebody put some twists on it, just like I did on Connor's arm. And of course, it wants to break. And so we took all of this and we turned it into a desire for 2 pieces of metal to slide past each other. Because keep in mind, just because it's rotating, that doesn't really change anything. It's 2 pieces of metal sliding past each other. It's no different if it's straight sideways than if it rotates. The only difference with rotation is the middle ones aren't doing any sliding past each other, whereas the outer ones are sliding wildly past each other and the middle ones are sliding a little bit past each other. But other than that, it's just metal sliding past metal, right? And so that 26.7 megapascals is something we could look up material-wise and say, will this material handle what we're asking it right there? Or is it going to snap off? Again, you can appreciate, I see why this calculation is done because we are rotating stuff a lot in our culture and we need to know if it can do it or not. So it's kind of cool, right? Well, let's take a look at this one. So this is, of course, exciting to me because this is a control for a small airplane. And this took me a second to figure out. So let me just highlight a couple things here for you about the picture so that you understand it. But notice there are 600 newtons pulling in this direction on a cable and 600 on this. And what is that accomplishing? Well, do you see that there's a pipe right here? And it's hollow. And by implication, the pipe is kind of looking like that. And so it's like, this is going to cause the pipe to rotate. Does that make sense? Now, why would that be in an airplane? Well, that's the elevator in the back of the plane, the part of the tail that goes up and down. That's what's happening right there. I need the tail to go up and down. And that's got a lot of wind pushing on it because I'm traveling 100 miles an hour. And, you know, it's like it's going to not want to do that with wind pushing on it. So again, that's a neat practical example of something that really does need to rotate in the real world. And so doesn't somebody have to pick, and I want you to stare at this because it's interesting. Doesn't somebody have to pick that piece of cable right there? And isn't that an axial load on it? And based on the last chapter, could that snap in half when you put 600 newtons on it? Yep. Let's make sure to pick the right cable so it doesn't snap in half. Now that doesn't snap in half, could we take that pipe right there and just twist it in half? That could happen too. We don't want that to happen. So chapter 5, let's choose some material that doesn't happen to. So I mean, isn't this kind of cool? And this is like fly the airplane. So this is kind of interesting. Okay. Well, this is like the last problem. It's a hollow pipe. And so this doesn't feel that much different. However, notice they didn't tell me a torque here. They didn't say, oh, the torque is 90. This time we're going to figure it out ourselves because we know torque is a force times the distance, and we have a force of 600 newtons, and we have a distance. So can we find the torque? I want to just give you a second to kind of think about this, like stare at the picture. Can you find the torque? And it might be nice to note, as I'm writing in the problem up here, if I kind of draw the center of that circle right there and call it A, what we really need to know is the torque around A. So this time it's not just a given, because torque very seldom is something, you know, twisting on someone's arm. It's caused by something like this, a force and a distance.
Would it be times 2?
Yeah, isn't that a wonderful question? It's not obvious, is it? Is it times 2? Do I have to do this twice, or do I do it once? Your book, and I did not emphasize this a lot, but this was back in statics. It's called a couple moment. Again, that is a really strange use of couple moment. Seems like that should be boy-girl stuff. Not for engineers. What's a couple moment? When those two forces are identical, and they're also the same exact distance apart. And the answer to Thomas's question is, yep, you got 2 of them there. But the good thing is they're the same. So you do 1 and double it. Are the units good? Yeah, like a minute ago, we ended up with kind of newtons and meters and stuff. And so there's, you know, part of me thinks we shouldn't leave that 75 millimeters alone. We should call that 0.075 meters. And so, you know, yeah, that's true. So if I take 600, and I want to emphasize something here because I did not emphasize this in class before. If I take 600 times 0.075 times 2, I get 90 for that. Do you agree with that?
Yeah.
Now, the shortcut of this is when I just multiplied by 2, I was thinking of it as 600 times 0.075, and then that was one of them, and then times 2. Do you understand that? But stop and think about this. Because algebra is commutative and associative, meaning it doesn't matter what order you multiply things. Would you agree I could have went 7 times 0.0 or 2 times 0.075 first and still got the same answer? So what we learned in a previous section is if you have a couple moment, meaning those 2 forces are exactly the same, all you really need to do is take 600 times the entire distance between them as a shortcut. Now, I don't like shortcuts because it's already hard enough for me. It's like I can figure this out based on logic, so don't give me any shortcuts. My brain is already full. But that was a whole section in statics that I kind of glossed over. But you may remember seeing that word. And it's like, oh, there's a couple moment here. It's like, what? You know, what does that mean? I don't get it. That's what's going on. So yeah, now we found our torque. It wasn't given to us, but we made it for ourselves. Great. Well, now we're on our way. The rest of this problem is like we just did, as long as we understand that this thing is hollow. So I say, okay, what did they ask me for? Did they ask for the same exact thing, like the shear max? They said determine the maximum shear stress. Oh, maximum. Okay, they didn't say like somewhere in the tube. They said maximum. Okay, good. That's what my formula is made for. Tau max we said is equal to the torque, 90 Newton meters, times the outer radius. What's the size of the outer part of that pipe?
30.
Notice it's 25 is the diameter of the inner pipe, right? And then there's 5 more. So it's really 12 and a half plus 5. It's 17 and a half. Like, it's not obvious, is it? Or you could say there's 5 over here, 5 over here, and 5 over here. So it's 25 and 10. It's 35. The diameter is 35. And then I cut that in half. It's actually radius 17.5 millimeters or 0.0175 meters. Do you agree with that? And then on the bottom, our J value, just like we did a second ago, it's always pi over 2. It's outer radius, 0.0175 to the 4th, minus the inner radius. The inner diameter is 25. So the inner radius would be 0.0125, 125 millimeters. You agree with that? And in the interest of time, that gives us a maximum value of approximately 14.5 megapascals. But then they asked something, which is why because in a sense, that didn't teach you very much relative to the previous problem, except for the fact that we had to find the torque ourselves. But notice it says also sketch the shear stress distribution over the cross section. You're going to see this question more than once. And so what the heck is that asking? Well, what it's asking is this. What we just figured out is there's 14.5 megapascals of force on the outer portion of that pipe, right? Now, what direction is it going? It's going perpendicular. So that's the 14.5. Now, where do you draw it? Well, anywhere you want to. Draw it over here, I don't care. But the key is it's heading out perpendicular. Does that make sense? Kind of like pounds per square inch, newtons per square meter.
So Doug, out of
It's
curiosity,
acting perpendicular. Go ahead.
We are finding the max shear stress by like basically using the max radius.
Yep.
If we wanted to find the shear stress of the inner radius, would we just use that? And it would be like, oh, like that's the max stress there. Here's the max stress for right at this moment.
Yeah. Did I pay you to say that? Because like that's exactly what I was. It's a wonderful question. So that's what's happening outside, right? But what's happening on the inside? Now, of course, all the material is the same, and the inner part's going to be less. And so there's part of me that says, who cares? Because if it's going to break, it's going to kind of break on the outside. Does that make sense? But well, in the case of the beam, though, I mean, yeah, the top fibers are working the hardest, but does that mean these aren't working at all? No, they're working too. So it's like, is there a way to calculate it? Yeah. So let's go calc that. What about tau? We'll just call it tau. I don't know, inner, I guess. Tau inner. Is it any different? The answer is no. There's still 90 Newton meters on it of torque. Because that was coming from way outside of it. There's still 90 Newton meters of torque, but what's the radius though? Is the location of the inner one still 0.0175? The answer is no, it's the inner radius, which was 0.0125. Does that make sense? And then the bottom part is identical. Can you track with that? Can you find yourself going, okay, that makes sense? The J hasn't changed. The desire that this shape has to rotate is made of the in and the outside part, but actually how much How much stress, how much shear stress is on the inner part? Well, it's just a different radius. So just to highlight it, one radius up there, one radius down there, everything else is the same. If I punch that, I get that the inner shear stress is 10.3. I can't read my own writing. I think that's a 10. 10.3 megapascals. Of course, it's less, right? And so then when I go over here to draw the entire, this is really cool, the entire stress distribution, well, I come back to the inner point and notice these vectors should be proportionate. 10 is about 2/3 of 14.5. So I'm drawing that one proportionally, just in my mind's eye, about 2/3 as long. Now, is that the only two radiuses in here? Is there metal other places? Yeah, there's metal all the way through it. Isn't there lots of radiuses? Well, the cool thing is watch this. If I just draw a line between those two, that's where all the rest of them are. In other words, they're spread all the way through this thing. Yeah, so basically by finding the minimum and the maximum, we sort of have them all. So you could actually stick in any radius you want between 0.0175 or 175 millimeters and 125 millimeters. You could stick in any radius you want and you could know what the stress was right inside there. Now, again, does it make sense the maximum is the one you're after, because that's the one that would allow you to look up in the back and choose the right material. So do you see the outer fibers there working harder? They're the longest lines. The inner fibers are working the least. If I kept on going, because this is solid, does it make sense it would go all the way to nothing in the center? In other words, this thing is actually emanating from right there. So because this is hollow, I'm done. But if it was solid, it just would have went all the way to nothing.
So the center has nothing until the outer fails, and then that force starts going towards the inner, and it becomes like a new equation. Right?
Say that one more time.
The inner has nothing as long as the outer holds. Because I was just thinking, like, if this failed, it's gonna shear right in half, right? Like the inner will fail. So once the outer starts failing, you kind of have a new shape, like one not as big a radius, and you start having force.
Yeah, I mean, it's kind of like every piece of metal in there is doing work. It's just the outer ones are working the hardest. But in the end, everybody has to fail in order for it to finally twist. That's exactly right.
It's like there's an integral in there somewhere.
Yeah, I mean, if you went toward something like, how much energy is required to do that, then it'd be like all of them added together. That's exactly right. So this is what I was referring to a second ago. Again, this is not hard. You're gonna look at this and go, this is totally easy. The only difference in this question is they're actually telling us, hey, this is like, I already chose my material. I already know the tau max, the tau allowable. I already know the number on the left this time. And so the question is like, well, don't twist it too hard then. So I don't want to twist this too hard so that it actually breaks. So this is, but it's the same exact formula. Now, this is what I was talking about earlier. Notice they said it's A36 steel. So I thought, oh, let's go look it up in the back. That seems like allowable. The shear allowable would be something. Remember that allowable shear was on the beams I showed you on that cool website. And I looked in the back and it was like, oh, it didn't list 60 megapascals. I thought it was weird they listed it. And then I looked in the back and it wasn't listed. Now I don't understand. But because they gave us 60, then they didn't really need to tell us what kind of material it was, I guess. So notice this says allowable, therefore I'm after the max here. And that's what 60 is. And of course, I'm thinking of that as 60 megapascals or 60 times 10 to the 6th newtons over square meters, since that's a Pascal now. And that equals T times C over J. So, what else do I know? Well, fortunately, in this problem, notice they gave us the torques, like I didn't have to calculate them myself. But which one am I worried about? Notice this is sectioned into two places. What does this area think is happening? What does that area feel? If you section it and chop it off right before it gets, because that's what a section was, right? You chop it off right before you get to that next one. Does it make sense everything in there is feeling 200? Now, if you looked at it from this side, does it agree? Yep, 300 going one way and 100 going the other is still 200. So it's got 200 on both sides. Just like when we pulled on a piece of pipe axially, we said if there's 100 on one side, there's got to be 100 on the other. Otherwise, it isn't going to be stretching, right? If I take and watch this carefully, if I take this pen and I lay it on my hand and I start twisting it, does it want to torsion? No, because there's nothing on the other side stopping it from twisting. So it's just rotating along and everything is happy, right? But if over here I say, no, I'm not going to let you, does it make sense if I twist this at 200, then automatically this has got to do 200 too, or it's going to start rotating in my hand. Does that make sense? So just this being fixed, it's not like I'm doing anything there, but if I come over here and go 200, then that means automatically I'm over here balancing that. You see what I mean? So it's like the right side's 200 and so is the left. And if you take 300 going one way and 100 the other, it is 200, isn't it? If they weren't equal like that, then it would not be twisting. I mean, it would actually twist. It would actually rotate, not fail to rotate. It's not going to create any internal stress in the member, right? What about in this section over here? What's happening between A and B? Notice it's got 300 over here, which means the pipe is experiencing 300 all the way through it until just before it gets to the 100, right? So it's 300. Now, is that agreed on the other side? Yep, because it's got 200 going this direction and another 100. So sure enough, it's 300 on both sides of that, isn't it? See what I mean? So it's like 300 and 200. One part of it's experiencing 300, one part's experiencing 200. Therefore, 300 is the torque I need because I'm looking for the maximum shear. And it's the same pipe all the way through. So that tells me it's going to break between A and B. That's my maximum. Tracking with that? Is that too fast to you? I don't think this is obvious. That took me a while to agree with that, I guess is what I'm saying.
I got it, but in a different way. So you said 300 minus 100 is 200.
Yep.
And
that's to get me to here.
Yeah.
And then that matches the 200 that's on the other side.
So I just looked at 200 and 100. Like, oh, they're going to match right there. So it's the same thing.
Yeah.
It's hard when it's not stationed on something.
Yeah. So I know the torque, I know the tau max. I don't know C and I don't know J. What is it asking? Their gears are subjected to the torques. Gosh, that's all they tell me. That's not good. I have two unknowns. All right. What kind of a pipe is this? Is it solid or hollow?
Solid.
This word right here is the only clue you have. It said it's a shaft, which is code for it's not hollow. So they got to tell us that. What is J equal to if it's hollow or if it's solid?
Pi over 2C4.
Oh, it's only got one unknown now. C. So I can solve that. So 60 times 10 to the 6th. And notice the units are all working. And then there's a C on top, but doesn't that cancel with one of the C's on the bottom? So now that's C to the 3rd. So if I just solve for C, let's see, I'd be multiplying by pi over 2. So I've got 300 divided by 60 divided by 10 to the 6th. Ooh, that seems like a big number. Everything else is multiplied to the other side. Then I multiply by 2, divide by pi. I got 3.18 times 10 to the negative 6. Then I cube root that. Notice you have to raise everything, the cube root, or raise it to the 1/3 power. So I'm raising this to the 1/3 power. I got 0.0147. because of the way I took care of my units, then this is in meters, right? Everything I did was in meters. So couldn't I call that 14.7 millimeters if I wanted to?
How did you cancel a C from the top?
Just because there's C to the first up here and C to the fourth down there.
You're into the 1/3 power, right?
Yeah. Because in the end, and I'll write this out just because it's algebraically kind of a pain, you really have 300, and then you multiplied pi over 2. Actually, you could leave pi over 2 on this side if you wanted to. You could multiply C cubed to the other side. You'd have to divide by 60 and divide by 10 to the 6th. And then pi over 2 is still down there. So I have C cubed equals some ugly number. The opposite of cube is either cube root, which is hard to find in your calculator, or just raise both sides to the 1/3 power. So I just had that decimal and said raise to the 1/3 power. Now, what did it ask though? It said, what's the required diameter? Interestingly, pipes are never designated by their radiuses in engineering. It's always diameters. That's not a diameter though. Does it make sense? You get it wrong in the back of the book. That's a radius. So if that's a radius, then I'd have to double it. And I'll remind you of this because I've showed you this before, but the symbol for diameter is like a circle with a line through it. You'll see that different places, and that's something you want at some point know. So I got 0.0294 meters, but of course that would be 29.4 millimeters. Do you notice this last statement in here though that I ignored up to this point? It said to the nearest millimeter. So it said, I want you to do it in millimeters, but then it also said to the nearest millimeter. So that means even 29.4 is not in the back of the book. What's in the back of the book? It's very important. Think carefully about this. If you could not order parts of millimeters, you had to pick 27, 28, 29, 30, 31, 32, 33. Like that's your only choices. What do you pick? You pick 30. You don't round off, you round up because 29 will break. You understand that? So even if it was 29.01, it would be 30. So we're going to see 30 in the back of the book here because you want to round up so it's strong enough, right?
Real world, 29 will break, but 30 will fit, right?
Right. Neither of them work. That's exactly right. That's what you're going to see in the back of the book. But it's not different. It's the same math we just did, right? But again, isn't that a very practical problem? In other words, if you design backwards, it's kind of like, okay, I already chose a material. I don't know why I already chose a material. It's got a certain tau allowable, and I've got a certain job I want it to do. Maybe these pulleys are running, you know, the air compressor for the AC unit inside your car, and some of the cool stuff that's in there. You got those serpentine belts that run all this stuff in there. And so I already know what I needed to do. And now it's like, well, pick a shaft that doesn't break then. I need it to be light, right? So I'm going to choose aluminum. I want it to be lightweight. It's a race car. So choose aluminum. Okay, great. All right. Well, then what diameter does it need to be so it can handle all that work? Very practical question. Beautiful question. All right. I think I want to stop there. I intended to teach 5.2. That was 5.2. I intended to teach 5.3 today, and I could easily squeeze it in, but you guys got a test to take over the last section, and that didn't feel terrible, right? I feel like maybe I can just ignore this and get the test over with, and I'll like figure this out over the weekend on Monday or something like that. So I think I'm going to squeeze 5.3 in next time and not say anything about it.